All right, so hopefully this new software makes it a lot easier for me to upload videos. One of the things that I like about it is when I click, you guys can see this little circle going on here. Another thing I like is I don't have to spend memory uploading and stuff. So this should be good. Hopefully this will allow me to put out more videos. All right. So our objective in this lesson is to apply the definition of similarity in terms of similarity transformations to decide whether two given figures are similar. So, like I said, we had skipped this lesson, which I think made the triangle things a little harder to do. So, this one will give us a firm definition on what similarity is. That way, that activity will make more sense. The activity will make more sense, and the module about triangles will make more sense. So, in geometry, there we have different size shapes. So we've talked about this before, unfortunately, because I skipped this unit. But it's this idea that you're just diluting things. So you're either making things bigger or you're making things smaller. So if your point of dilation is like here, for example, to get to this other side, you're going to like increase the distance. So let me see. Let me grab an eraser. The thing that I'm still going to get used to is changing the colors. So let's say your point of dilation is like way over here. And what will happen is you're just increasing the size, the distance from the point of dilation, which makes it look like it's getting bigger. So by increasing like certain points, it ends up making everything look bigger. So let's see how that goes with the activity. So, oh, you can just wipe this. Oh, I'm gonna like this one. All right, so let's get into this. So similarities, although, so again, it's just this idea of things either getting bigger or smaller. That's mainly what similarity is. It's the same it's the same shape. So the angles are the same, but the sizes are not. So right here, what we're gonna do is we're gonna talk about certain shapes and how we can map them on there. So when it comes to this, I find this very weird that they're kind of making you guys go through this. So luckily, we're just going to go over these. So what's going to happen here is we're going to find ways to map these on. So this is my basic idea here. This idea, or this is my pre-image. This A, B, C, D, E is my pre-image. And I'm going to try to map it onto each one of the image. So remember to describe each transformation completely. For example, you must specify the line of reflection, the center of dilation. For each dilation, perform the transformation to check your responses. So, for example, if I want to map, let's see, if I want to map this onto here, what I would do, first of all, is I would have to reflect this off of the x-axis because I want to flip this upside down. Actually, looking at it, if I reflect it over the x-axis, what will happen here is we get this shape. So it's not quite the x-axis. It actually looks like we're rotating 180 degrees. So when we learned about transformations, remember how 180 degrees kind of flips everything over? One of the rules for flipping 180 degrees was, uh, give me a second here, your X and your Y, if you're flipping 180 degrees, rotation of 180, what happens is we end up swapping everything. So the X and the Y swap places and everything becomes negative. So let's do that. So give me a second here while I start rotating this just to get this going. Yeah, I want to change that. Undo. Okay. So I'm going to make a point right here at the center. And luckily, because of how they named everything, they actually skipped the letter O. And I think the reason why they did that is to let me put the O right here at the origin. So I'm going to try rotating everything 100 or this 180 degrees. So go here. I'm going to go to my mapping tools and I'm going to reflect around the point. So I'm going to do this. I'm going to reflect this point and I'm going to reflect it 180 degrees. See if that kind of gets me to that figure. Oh, clockwise or counterclockwise doesn't matter for this because 180 is the same way clockwise or counterclockwise. So if we look here, okay. So if we look here, we see that our shape did in fact flip over in the same direction. Now the only issue I have here is how much smaller is this? Well, to do that, I'm going to look here and I'm like, oh, this is about half a unit from, or I should say one, because apparently these are by twos. So this is 1 unit, this JI, and right here, this EI is about 2 units. So I'm going to see if cutting it in half helps. So what I'm going to do here is I'm going to go to my tools. I am going to dilate from a point, and I'm going to dilate from the origin. So from here to here, how much am I dilating it? I want to cut it in half. So I can either do it as 1 divided by 2, or I can do it as 0.5. I'm going to try 1 divided by 2, see if it, GeoGebra understands it. Oh, so it looks like that works out. And then I'm going to want to translate this to see if this works. So let's translate by vector. I'm just going to grab the shape and I'm going to move it. And it looks like it maps on perfectly. Okay. So now I have to describe everything I just did. So rotate 180 from O comma O. And I like doing everything from the origin, from the 0, 0 point, just because it's like easier to do and understand. So I'm going to rotate from there. And then I'm also going to dilate by a factor of 0.5. And that's just saying I'm making it smaller by half. And then I'm going to translate it. I'm going to translate, and the way I'm going to show translation, I'm going to do it with brackets. I'm going to describe how much I moved my x value. So from here, I moved from -2 all the way to 6, so I moved 8 units. So for my x, I moved 8, and it was to the right, so that's why it's positive. And then I'm at 0, and I want to get over here to this j. So this j, if I zoom in, I see that j is at 3. So from 0, I went up 3. So this is what it means by being specific. I said I wanted to rotate. I said where I wanted to rotate from, because where you rotate from matters a lot. So let's say I had like, I don't know, a triangle here, and I wanted to rotate about this point 180, then my shape would look like this. Well, I made it bigger, but let's pretend I know how to draw. But let's say I did a different point of rotation from over here and I rotated 180. Well, if you can see here, the distance from here to there is quite a bit. So when I would draw this shape and I rotate 180, it would be way over here. And again, let's pretend I didn't do anything. So knowing where we're rotating from does affect how it moves. So I like doing everything from the origin. It just makes everything easier, but there are some times where you want to rotate, you want to keep stuff the same. Is that making sense so far, everybody? Everybody kind of get that? These, again, like I said, just answering these does take a while. And the reason why they say answers may vary is literally because everything kind of changes. It depends on your opinion. I could have easily just said, I'm going to move this over. All right. So now I don't want to have all of these shapes here. So before I close this out, I am going to share this. Share. First, I have to save it. I swear these start taking longer and longer to save. I guess because there's so much stuff there is to save. So I'm going to copy that, paste that here, just so there's a record of what I did. And then I don't want to have all that stuff there, so I'm just going to close this out and do the next one by just clicking transformations again. So now I already did the F. So I want to do it for the KLP. So if I look at KLP, where is KLP? It's right here. It looks like I'm just increasing the size. So what looks like we're doing here, oh, it's not just increasing the size. The reason why I know this is, watch this. If I increase the size from the origin, what would happen is this E, the distance here is 4. So if I increase the distance from the origin, I would have to end up here, but I'm not. So what's happening is we're kind of increasing the distance from somewhere possibly over here. Let me change colors for that. Possibly over here, because then this distance starts coming out over here. Well, that to me, that's complicated. I don't want to deal with all that. So what I'm going to do is I'm just going to move this down and then make it bigger. Or I can make it bigger and then see and then move it. Oh, that's probably better. I'm going to do that. Work smarter, not harder, guys. So whenever you're thinking about this, like I said, I could have moved this a little bit negative and then done that, but to me that's harder. So what I'm going to do is I'm just going to increase the size of this. So from K to L, that's the size of, oh, actually, let's use our tools to figure that out. What's the length of K to L? And apparently this doesn't like me. K to L, oh, K to L's 4. I can't believe I didn't see that earlier. So K to L is 4. And this, oops, why did I get perimeter here? Oh, I know why. I clicked the shape instead of the line. And this is two. So basically, this distance is just twice as big. This is 2, this is 4. So I'm going to dilate it by a factor of 2. So I go to my transformation tools. I'm going to go to dilation. And I forgot that I don't have an origin right now. There we go. So I'm going to dilate this. So let's go to dilation. I'm going to pick this point. I'm going to pick this shape. I'm going to do it by a factor of 2. So here we can see what happens by just making it bigger. Well, that's not enough. I also need to translate this. So I'm going to go here, translate by vector. I'm just going to grab the shape and move it right there. So by doing this, I now know that I have to dilate from 0, comma 0. Notice how when I talk about a point, I use parentheses. When I talk about like a translation, I kind of use brackets. I just do this to kind of differentiate it. Oh, this one I forgot. From 0, comma 0. I'm dilating it from 0, comma 0 by a factor of 2. I made it twice as big. If you guys are having trouble like understanding the words I'm using, let me know. And then what I did now is I translated it. So now I translated, so I moved it. I'm going to move this from here to here. So I moved it. Let me zoom in a little bit to kind of see the numbers. As far as the x goes, I moved it from 0 all the way to 4. So I moved it 4, comma, y I moved down. So I went from 8 to 6. So from 8 to 6 to get this new point right here, that's going to be a negative 2. So minus 2. All right. And now we can move on to the next one. So again, I'm going to save my thing. You guys should also save it, not just to prove your work, but also to kind of take pride in it. Um, these problems take a while to do. So by saving it onto your account, like you're showing that you know how to do it. That one there. All right. And then, oh, did it save the same link? Oh, hopefully it doesn't overwrite it. All right. And the next one we're going to do here is QRT. So let me get rid of this one. We're done with it. Open up a new one. This is what I meant by like, yes, it's a little bit of stuff, but just doing the transformations is honestly going to take a while. Oh, no, I don't want a number line. So now I want to do this one. So let's take a look at the distance. How far apart are these? We already know that this one is 2. So just to kind of measure this, that's 2 apart. This right here is 1.25 apart. So we can make this smaller. So the idea here, remember, it's always new over old. Whenever you're doing scale factor, new divided by old. So in this case, our new is 1.24, 1.25, and our old is 2. Well, I don't really like this whole like decimals and fractions thing. Although what's nice about having it like this, I'm going to leave it like this and you'll see why this is actually kind of useful having it. I'm not the biggest fan of having it normally, but it's actually really useful to have it this way because of scale factor. When we do a scale factor on GeoGebra, they're actually really nice and they'll do all the calculating for us. So I'm going to start at the origin. I'm going to make this smaller by this factor I just made up here. So you don't even have to do algebra to figure this out. You can actually do it just, so I'm going to dilate from point. So I'm going to dilate this shape from this point, and I'm going to do it by a factor of 1.25 divided by 2. Make sure you have your divided by 2, otherwise you're going to end up making this bigger. And then I have this shape right here. So let me try to translate this. So I'm going to grab my transformation tools here, translate by vector, and I'm going to move from here. Oops, I accidentally clicked the line. Undo. Grab the shape, not the line. Come on now. Translate by vector. There we go. And I'm going to try to move that here and line it up as best. So I see here that it didn't translate properly. From what it looks like here is there's a different lengths going on. So even though my A and B match up, I can't get anything else to match up because my T and U aren't to scale. So these two are not similar. So what I would do here is I would say that I dilated by factor of 1.25 divided by 2 from 0, comma 0. So I did that, and I also translated, but could not get all points to line up. And we'll talk about why this happened. So basically, they're just not similar. Dilated. That was weird. All right, so let's take a look here. So now we're going to do the last one. So let me save this one just to save my work. Here, I'm going to call this 3. Get my link. All right, copy this. I think I might have accidentally not clicked the copy button. So unfortunately, if anywhere more to copy this, it'll be the wrong picture. Make sure you guys don't do that when you do it. All right, so I'm going to cut this out because all of these are different problems. So I might as well start off with a brand new template without having to hit undo. All right, so my last one. So obviously this one, it looks like what's happening is it's just reflecting from here to here. It's just upside down. So let me do that. So let me just do a reflection. It's upside down, so I'm just going to reflect it. Go to my transformation tools. I'm going to reflect about a line. So I click the shape that I want to reflect. I click the x-axis, and I see, it looks like this one's smaller. Let's see how much smaller. So I'm gonna undo that for a second because I should make this smaller. Making the dilation is easier just because if you dilate it, then you can do all your translations easier. So let's find the shape of this. So I'm going to distance this and this. So it looks like my new, so always remember your scale factor is always new divided by old. And my old was this. So this is a similar scale factor, but this one's 1.5. So let me scale this first. Does everyone understand why I'm making the scale different? Anybody have questions on why I'm not reflecting it first? That was like a mistake on my part, but it's easier to just dilate first. All right. So let me just start dilating. So from here to here. Come on. Dilate from point here to there. There we go. And again, we're going to do new divided by old. So if I'm doing new divided by old, my new is 1.5. My old was 2. Where's my dilation? Dilate from point this to here. 1.5 divided by 2. There we go. So this should be the same size. See how it's 1.5 and 1.5 now? So now let's do the reflection. So go to my transformation tools. I am going to reflect. So I grab this, reflect it from here. All right, cool. So now I have a reflection. Now all I have to do is translate. So go to transformation tools, go to your dilation. I know I keep calling this transformation tools. It doesn't say it anywhere. It's just these are all the different types of transformations we can do. So that's why I keep calling it that. So I am going to translate this. I'm going to move this. I'm going to grab this. I'm going to move it here. So if I zoom in, I can actually see how much I moved. And it's actually good because I can still line it up a little bit better too. And this one looks like it landed spot on, unlike that last one. So if I look at my movement, I moved one to the right and one down. A pretty simple transformation. So first thing I did was reflect. Oh, no, first thing I did was translate or dilate by a factor of 1.5 divided by 2. Then I reflected about the x axis. And then from here, what I'm going to do is I reflected, so now I need to translate. So I translated. And I translated, I went right one, down one. Right one, down one. And that maps them all out. And again, take pride in your work, guys. Share it. Don't just share this for me. Like I said, you worked hard on these. You should have the work saved somewhere. All right. So now it's going to be like based on your work with similar transformations of question 1, which images are similar? All of the images are similar except, what was it? QRSTU. Because oops, I don't know how it became italicized, Control I. Because I could not make all the points line up. Right? And then here it's going to be like often there is more than one set of sequences that will take a preimage to an image, determine one or two other sequences created from this. Okay, so one or two, for time's sake, they're telling us one or two. We technically already created one, so I'm not going to spend time creating another one or another two. I'm going to create another one, and that kind of classifies as doing the two. So what other sequences? Well, instead of rotating 180, so let me kind of start from the beginning again. Let me make another transformation. Closing that old one because I don't want my computer super slow. Oh, did you say something before? Oh, okay. Is everything making sense so far? Okay. All right. So the last one we're gonna do is, give me a second here, is we're gonna find another way to get this FIG. So I rotated 180, but another way I could have done this is instead of rotating at 180, I could have reflected off the y-axis, reflected off the x-axis. So let me do that. So first, like I said, dilation, I think that you should always start with dilation. It just makes it easier. So let's figure out how much we have to dilate. So in order to do this, I'm going to use my measuring tools here. I know it doesn't say measuring tools, that's what they do. I'm going to measure this AB, and I'm going to measure this, because these are basically corresponding. So I have 2 and 1, so I have to cut it in half, which I should have remembered from the last one. So I'm going to dilate this from the center. And of course, I need to put a point there first. So dilate this from the center. I'm going to dilate 1/2. And then from there, what I'm going to do is I'm going to reflect. So go here, reflect about line, here to here. I didn't click the whole shape. This shape to here. Oh gosh. I'm sorry, guys. This shape to this line. There we go. And now I'm going to do this shape. I'm already on the reflection tool. To this line. See how it's the same as if I rotated 180? It's just a longer way of getting there. I could have also done this shape to this line. That's why I think they say 1 to 2 more, because you can technically do it reflect, reflect this line, or reflect this line, then this line. Doesn't matter. And then from here, I'm going to translate. So I go to my transformation tools, translate. I'm going to go up a lot. Oh no, I picked up 1 point. Come on. Click the shape. I'm going to go up. Come on. Click the shape. Okay, there we go. So let's figure out how much I moved. So if I'm looking at this, I'm going to start at this A, because to be honest, that makes it a lot easier. So I'm going to go from A to 7. So I'm going to translate. I know it's the last move, but I'm going to write the last move first. Translate 7, and I'm going to go up. So I start at -2, and I'm going to go all the way up to 1. So that means I went up 3 spaces. And before I did all that, let's start from the very beginning. I dilated by a factor of 1/2 from origin. Then I reflected out y-axis. I did the y-axis first. Then reflected about x. And if you really want to get credit for that other one, luckily we did the rotation first. You guys can literally just copy this and just go like, I reflected about the x-axis first, and then I did the y-axis. Because of how I did it, because of the fact that I dilated first, I can do either or, and it'll still be the same answer. All right, so moving on, the calculation part of this does take a while, and this looks intimidating, guys, but I want you to see that it's not that bad. All this is the Pythagorean theorem. I've said it several times. I know I'm going to keep like repeating myself, but honestly, it just makes things easier. If I said this was a squared plus b squared equals, I'm going to say d squared, just so we can keep this d idea here. If I wanted to solve for d, I would take the square root. So I would get the square root of a squared plus b squared, right? Well, what's happening here is this is my A, and this is my B. So if I looked at it through a triangle lens, and I wanted to find this D, I'm just taking my X values and my Y values here. That's all I'm doing. So it's a Pythagorean theorem. finding the distance is just the Pythagorean theorem. So let's figure this out. So if I were to figure out AB, first of all, I don't even have to calculate that much because I have no y. Because I have no y, it's just x squared, the square root of x squared. So if I were to calculate this, I would calculate like this. Square root of x squared, which is 4. Like that's just 4. Oh, 4. 4, then square root it, which makes it 2. 2 squared is 4, square root is 2. GeoGebra just said it was 2. Cool. Now we're going to do FG. Well, if I look at FG, let me just undo all of this. That was a bad idea. Okay, cool. There we go. So if I look at FG, I'm looking at this one. Well, if I look here and I zoom in, I see that I have no y. So it's just 1. What's going to happen here is I'm going to take the square root of 1 squared plus 0 squared. Why am I going to even write that down? So this equals, oops, get out of the square root, equals 1. And then GeoGebra is just going to say it's 1 because we've done it before. Now we're going to do BC. I don't know how GeoGebra was expecting you to calculate all of this. Or I don't know how GeoGebra was expecting you to transform all of this without doing these ratios before. So I have no idea. They should have taught you about new versus old a while ago. Oops. All right, now we're going to do BC. So BC, if I look here, I have no x and my change is 1. So in other words, it's square root of 1 over 1. The 1's just referring to a y this time instead of an x. And this is a 1, GH. So GH is this right here. So if I look closely, again, oh, this one's different. Hang on here. Okay, so this is 0.5. There's no x, there's no y, it's just 0.5. We're going from 1 to here. So in other words, my rise is 0.5. There's no run, so it's just 0.5. So what I'm going to do here is I, being lazy, I'm going to copy this, paste it. But if you click this, if you highlight it and go here, you can actually edit the equation. So I'm just going to edit this to be 0.5, which means this is 0.5. And GeoGebra is just going to say it's 0.5. So what I mean by that is if I were to measure this, GeoGebra would just say it's 0.5. Right now they're asking us easy ones. Hopefully we get to a hard one. All right, so now it's asking for CD. Oh, here we go. Now we have an interesting one. So let me clear the board of the ink. So if I look here, let me zoom in a bit. If I, oops, come on. So if I zoom in, I see that going from here to here, I'm going from 3, so this is a 1. And then looking at my run, I'm going from here to there. So I'm going from this 2 to 4. So this is a 2. So when I'm doing this formula, I'm going to go take the square root of 1 squared plus 2 squared. And this is the same thing as the square root of 1 plus 4, which is the same thing as square root of 5. All I'm doing is I'm leaving my mouse here, so it's easier. I just have to tap it to get the answer. And let me use a calculator. So I recommend you guys use the Google calculator. It's pretty good. It doesn't become a problem until you get to like algebra two, late algebra 2. Square root of 2. So I get 1.41. So my answer for this one would be 1.41. Or if I want to be a little more detailed, now we can see what GeoGebra is going to say because we haven't measured this on GeoGebra yet. Grab this, and GeoGebra says 2.24. Did I do something wrong here? 1, that's 1. Went from 2 to 4, that's 2. Square root of 5. I did the square root of 2. Oh my gosh. Guys, wake me up here. 2.236. 2.236. So let me edit this because I didn't realize square root of 5 is bigger than the square root of 4. 2.236. And GeoGebra just translated that into 2.24. They simplified it a little bit. So that's all we're doing here. We're just doing Pythagorean theorem. Ooh, I don't even know if we're going to be able to finish the first activity for this one. So just to move on a little faster, you guys can see how I'm doing the work. The next step, it's going to ask us to find the ratios of these. So basically what's going to happen here is after you fill out all this chart, let's say we're going to do the ratio of FG over AB. So in other words, they want to do new over old. So new is 1, the old was 2. So FG, we said was 1, and AB was 2. So we're going to do this 1 over 2. Then we're going to do the GH and BC. So GH, so 0.5 over BC. BC was 1. So in other words, 0.5 divided by 1, well, that's just 0.5. That's also 1/2, in other words. You'll see why this matters later. I'm just going to call it 0.5. And 1 divided by 2 is also 0.5. What they're going to end up showing you is that everything changes size by 1/2. So here, based on your work, so again, just finish up this part. I'm just running low on time here, guys. I'm sorry. I know it takes a while with my explanations. Hopefully it is helping you guys. Based on your work here, 1 through 5, what is a similarity transformation? What is necessary to determine whether the two or more shapes are similar? Explain in terms of rigid motion, transformation, dilation. All right. So what's happening here? So what we notice here is when the shapes are similar, all the proportions are the same. So that's what I mean. To be similar, the idea of being similar, what is necessary to determine that the two shapes are similar? Explain in terms of rigid transformation. Oh, so explain in terms of rigid transformation dilation. So when shapes are similar, you can map one shape to the other through dilation, because that's what we've been doing. We've been dilating through dilation and rigid trans transformation. So that's all we're doing here. We're just dilating and then transforming it. Rigid transformation is just the idea of moving. All proportions should be similar. And then write down what you guys were having trouble with, if anything. I would honestly, like, had I not known what all this was, so I imagine it'd be hard for you, I would just write something like, um, I don't know how I was supposed to dilate without knowing the idea of ratios. Because that's the thing about Edmentum, they try to like make you come to the conclusion on your own, which is normally a good idea, but it's these very abstract, complicated ideas. So I'll leave that here. All right, so moving on to slide 7. So the idea here is this idea that you can dilate and move stuff. So for example, the two polygons here, 1 and 2, are similar because they have the same shape, and we can just dilate and translate to make it work. But polygon 3 is not similar. The shape's totally different. Look at how different the angles are and everything. So polygon 1 is similar to 2, but not 3. All right, so now we're going to deal with this shape right here. So we dilated this and rotated transformation. The endpoints are, these are the endpoints, and the endpoints of the translated one are this. What is the scale factor? So what they want us to do here is they want us to find the lengths. So remember, it's always going to be new over old. So first we have to find the lengths. But this is going to be our end goal, finding the new over old. All right. So let's do this. So if we're doing this, I'm going to use some different colors. I'm going to go from here to here. So I know that my x is 8 squared. And then I want to go from here to there. So I'm starting from -7. I'm going all the way to 8. So in order to get from -7 to 0 is 7. In order to get from 0 to 8 is that. So I went from -7 to 8. I did a little pit stop here at 0 to make it easier for me. 7 plus 8, I moved a total of 15 spaces. So when I do this, I'm going to do the square root of 64. And luckily, for some reason, I have 15 times 15 memorized is 225. It's honestly from a cartoon show that I don't know why that line just stuck in my head. It's from Batman Beyond, in case you guys have ever seen Batman Beyond. Harry's trying to prove that he memorized the multiplication tables. And it's like, what's 15 times 15? 225. All right, so, and that's honestly the only reason why I know that. So we have this 289. Let's see if this has a nice square root. 289. I doubt it. Oh, it does. 17. That's nice of them. So this all equals 17. So this was our old. Now we have to find our new. So in order to find our new, we're going from 6 to 2. So if we're going from 6 to 2, we went -4. And then we're also going, so that was our rise, or our run, sorry, that was our x. And our y, our change in y, -6 to here. So we're going to go down, we're going to go up 6. So from going from -6 all the way to 0 is 6, but then we're also going to hop over to 1.5. So sorry I'm going so fast. I know we're late on time. That's why. So from here, what I'm going to do is I'm going to change this to 7.5. So I'm going to do so plus 7.5 squared. And I'm going to type that into my Google calculator because I want to just get this done in one go. So I'm going to hit the square root of, give me a second here. Let me do this. -4 squared, and then plus this 7.5 squared. Oh my gosh. They're really doing something here. All right, and then I'm going to close the parentheses. So the first set of parentheses is for the square root. Second set is just to make sure that I'm squaring the negative. The other set is just out of force of habit. I like putting parentheses when I'm squaring stuff. And then I'm going to close the square root. This here, we get 8.5. So this length here should end up being 8.5. So I have 8.5 divided by 17. That's my new divided by old. All right, so let's take a look here. Nope, not that calculator. 8.5 divided by 17.5. All that work just to say it's half the length. My gosh. All right, let me clear this out. And the ratio here is going to be 0.5. Yep. And they make it seem all easy. It's like, oh, it's 1/2. Obviously, come on. This stuff does take quite a bit of work, guys. All right, um, so let me stop the recording.